All right, so can you see the screen?
Yes.
And Cameron continues
Yep.
the sequence of smart-ass comments that we have come to know and know.
It's recording, right?
It is recording.
Okay.
All right. So what I want to do is the last major, topic that I really want to cover is Taylor series. And the idea is, given f, approximate f with a polynomial. And the idea is, the more terms we have in the polynomial, what do you think is going to happen? As we take more and more terms for approximation, what do you think should happen?
Get more accurate.
It should get more accurate. And so we have the 0th order approximation. And so all we know is we know the value of f of 0. That's it. That's all we know. So at time 0, you are a certain distance from home. What would be your best guess? So t0 of f, I need a function of x. We know it should equal f of 0 at 0. And that's all I know. So what would you guess its value is for other points? So if I tell you at time 0, you're 5 miles from home, what would you guess your distance is at 1 hour or 3 hours or -1 hours?
No further than 5.
5.
Anything? Oh,
This is your best guess. You have no information. You don't know if you're getting further away or if you're getting closer, right?
Just staying where you are.
Or if you're staying where you are. That if all you know is your instantaneous location, your best guess is that that's where you stay forever. So then we have the first order approximation. So now we know f of 0 and we know f prime of 0. So we know our location at time 0 and we know our speed. So now, what do you think our guess might be?
Will that just be the f prime of 0 x plus f of 0?
Yeah, and normally we write it in ascending order like this, but yeah.
Oh, okay.
So this
I was
is
thinking
yeah.
like that's like what
Right.
A line would be.
And so
mx plus
no, that was really good. So if I give you something like this, I'm looking at the best fit approximation, or the best fit line at that point. Is t1f of x is f of 0 plus f prime of 0 times x. This is your start. This is your speed. And this is elapsed time. So this is the tangent line.
Yeah.
So we've seen this before.
Yeah.
Let's get a little bit more interesting. What do you think we should have for the second order? What information?
well, speed.
We have f0, f prime of 0,
Direction.
not direction,
second derivative, f dou prime of 0.
acceleration. And this is the part that's tricky. So we know it should start off as f of 0 plus f prime of 0 times x. Anybody want to guess what comes next?
I mean, think f double prime of 0 times x, but I feel like that's not times x.
Would it be times
I'm-
x squared?
Ah,
X squared,
good.
yeah.
X squared. So it's not quite that. It's close. You have to
Two.
divide by yes. But a better way of writing 2 is 2 factorial.
Okay.
And here, this is x to the first, and we're going to divide by 1 factorial. And in fact, you could even view the first one over here as dividing by 0 factorial.
So is this like the geometric? Wait, no,
It's
the
not
E?
geometric. It's similar to E.
that's what I meant.
And so if you had to guess for the third order,
Well, obviously you have that.
so it'd be, t2f of 0. I'm sorry. It's not be 0. This should be of x. Sorry. So what would you guess would be the next term?
Plus f prime triple prime.
Yep.
0 x cubed over 6 or 3 factorial.
3 factorial. And in general, we write this to mean the nth derivative of f at x. And the reason is Roman numerals eventually suck, and your primes suck, and it gets painful to keep writing more and more primes. So let's just talk a little bit about why this might be good. So let's consider.
Wait, Dad.
Yeah?
Could you do prime? Like, would it be 4 prime or would it be IV?
So people do both. So people do sometimes do FIV of x for the fourth derivative as f quadruple prime of x.
Just wondering. And
yeah.
like same thing with 5.
Exactly. It just gets painful to write all that.
But let's be real. How do we use factor?
So let's consider, and I'm just going to do this case to give a sense of what's going on. F of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial. Okay, and we want to compare this to f of x. Okay, so what's the most natural place to compare them?
Sure.
Yeah, at x equals 0, what is t2 f of 0? When I plug in, what do I get?
F
F of 0 and f of 0, I guess, and f of x is f of 0 at x equals 0. So do we agree that they both agree when x equals 0? Just good. So now let's take derivative. Derivative. So what's the derivative of the function t2f? So what's the derivative? Let's go into order. Simon, what's the derivative of f of 0?
Like f prime of 0?
Nope. F of 0 is a number.
Oh, like a constant.
Right, f of 0 is a constant. So what's the derivative of
So
any?
0.
Yeah, this is one of the this is one of the most confusing things people find in calculus, is when I write something like f of 0, it's now just a number. So the derivative of f of 0 is 0. So Zeke, what's the derivative of f prime of 0 times x?
F prime of 0 plus a constant times x.
Just
Nope.
plus a constant. Right?
Nope.
No, it's just f prime.
It's just f prime of 0.
Oh, right. Oh, yeah, that makes sense. Yeah.
Right? So if I give you the
Constant.
function,
Yeah.
if I gave you the function x, what's the derivative of the function x?
F prime.
No, if I give you
Wait,
the
oh,
function
x. Wait, derivative function, right, is 1.
It's
So,
1. And if I give you 2x, its derivative is 2. If I give you 3x, its derivative is 3.
yeah, so it's just a constant.
So for the next one, we have f double prime of 0. What's the derivative of x squared over 2 factorial?
2x over 2 factorial.
Over 2 factorial. Okay.
The
So
2's cancel. Can
the 2's cancel. At x equals 0, what is t2f prime of 0 when I put in x equals 0?
That.
So when I take x equals 0, what do I get? I get f prime of 0. And when I put in x equals 0, what does the second term equal?
0.
Yes, it's just f prime of 0. Good. So look, we're trying to compare it to f of x. They have the same value. They have the same distance at 0. They have the same speed at 0. What should we look at next?
Sure.
Yes, second derivative. So we need t2f double prime of x. So Simon, I think it's your turn. What's the derivative of f prime of 0?
Wouldn't still be 0.
It would still be 0. And then Zeke, what's the derivative of f double prime of 0, 2x over 2 factorial?
It's just, wait, this seems oddly familiar. Like,
So what's
f double prime of 0 times 2 over 2 factorial.
or actually 2 times 1 if you want over 2 factorial, right?
But that just is 1.
But that's just 1.
Yeah.
So at x equals 0, t2f double prime of 0 equals f double prime of 0. So what we've done is, T2f of x is f of 0 plus f prime of 0x plus f double prime of 0 x squared over 2 factorial. At x equals 0, same value, same speed, and same acceleration as f of x. So what we've just done is we've approximated our function with a polynomial, with a quadratic here. So if my function, it looks something like this, what I'm doing is I'm finding the best parabola that approximates it nearby. And so the idea,
So if it is a parabola, you would just look at it.
so if it was a parabola, right, so if I give you f of x is, let's say, 2x squared minus 3x plus 5. Okay, let's calculate it. What's f of 0? 5. Does everyone agree it's just 5?
Yeah.
What's f prime of x? So Cam, you do the first term.
Oh, that'd be 4x.
4x. Simon, what's the next term?
3.
And Zeke?
Well, 0.
And so what's f prime of 0?
-3.
-3. And now let's look at f double prime of x. So what's the derivative of 4x minus 3, Cam?
It's like the 4.
4. And so f double prime of 0 is
4.
4. So if we now look at the Taylor approximation, that's f of 0 plus f prime of 0x plus f double prime of 0 x squared over 2 factorial. When we put things in, f of 0 was 5, f prime of 0 was -3, -3x, and then we had f double prime, which was 4 times x squared over 2, and that does simplify it to 5 minus 3x plus 2x squared. So if you have a parabola, it becomes perfect. So what I want to do is I want to take, we're going to end with either sine or cosine. Which would you like to do?
Cosine.
Cosine. So let's take f of x as cosine of x. So this is a fun one. What's f of 0?
1.
1. Everybody agree cosine of 0 is 1?
Yep.
Okay. And remember, what's the derivative of cosine?
Minus sine.
Minus sine of x. Excellent. And what's the derivative of sine of x?
Cosine.
And we have to be working in radians for this.
Yes.
So what's f prime of x? Well, it's minus sine of x. What's f prime of 0?
0.
0. What's f double prime of x? What's the derivative of minus sine of x?
Negative
Minus
cosine.
Good, negative cosine of x. And so what's f double prime of 0?
-1.
-1. F triple prime of x. What's the derivative of minus cosine?
Sine.
Sine of x. And what's f triple prime of 0?
0.
0.
0. And then I'll use the Roman numerals. What's the derivative of sine of x?
Cosine.
And what's the value here?
It's 1.
So what do you notice?
It went back to the original function.
Yeah. So this is a really good observation.
It's a loop.
It's a loop. We have cosine of x, which is what we started with. So it goes 1, 0, -1, 0, 1. What comes next?
0, -1, 0, 1.
Which, of course, that makes sense in the context of
Yeah.
the trig function, right?
Yeah.
Yeah.
Because, like,
It's true for sine.
Mhm.
Yeah, this would be true for sine.
So
You're
sine
just
would-
starting it here
Sine would just
instead
start
of
there.
starting it up
Exactly.
there.
And so what we now get is the following. so I'm going to just use this notation. The infinite Taylor series is the sum, and it goes from 0 to infinity, of the nth derivative at 0 over n factorial times x to the n. So 1, does this sum converge? 2, does it equal f of x? And what's interesting is there are situations where the sum does not converge, and there are situations where the sum converges but does not converge to f of x. Things can be tricky, but for the problem we're looking at, if we take f of x equals cosine of x,
That converges.
it converges. And in fact, what we get is the infinite Taylor series in this case is 1, and there was no x term because it was 0, minus x squared over 2 factorial, no x cubed term, plus x to the 4th over 4 factorial, no x to the 5th term, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial. I guess not going to be minus, dot, dot, dot. It turns out that this series converges and converges well. Next semester, I'll actually show you some animations about just how well it converges. But this does a phenomenal job.
Wait, converges means goes back to 1.
So no, what do you hope this converges to?
0.
Nope. Converges to, so this is the Taylor series of which function?
Cosine.
So what do you hope it converges to?
1.
No.
Cosine.
Cosine
Oh, yeah, that's right.
converges to cosine of x.
Oh, yeah, I was thinking it would be converged.
Yep. And let's just do, I guess, one more. We'll do it really fast. So let's let f of x be e to the x. This is probably the easiest one I can give you. What's f of 0? What's e to the 0?
1.
1. What's f prime of x?
E to the x.
Let's assume we somehow know the derivative e to the x is x. What's f prime of 0? 1. What's f double prime of x?
E to the x.
What's f double prime of 0?
1.
So 1, I think.
Yeah. Do I have to continue?
Yes.
No. F triple prime of x
Regret
is e
saying
to the
that.
x. F triple prime of 0 is 1. Do I have to continue?
Yes. We did both the last ones.
And in a shocker, the fourth derivative
It's different.
is e to the x. Actually, I did a research project run through. It wasn't until the 8th that things actually started looking different. Yep.
Why not the 8?
It was very technical. So we get that the infinite Taylor series for this function is just the sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial times x to the n. So it's just the sum, n goes from 0 to infinity, of x to the n over n factorial. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. 4 dots? 4 dots. And so, 3 dots. And so, well, the fourth dot was at the end of the sentence. And so, this is just a quick introduction to Taylor series. Okay? This is the last of the really powerful applications of calculus. It allows us to replace complicated functions with simple functions with nice polynomials. But the big problem is things do not always converge. And so, with then we have for Thanksgiving is either the best or the worst real analysis. Nope. This is a very interesting function. So f of x is defined as the following. It is equal to e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. If you were to plot this function, and again, we'll look at this later function is extremely flat near the origin. The reason is you have e to the negative 1 over x squared. If you take x equals 1 over 1,000, you have e to the negative 1 divided by 1 over 1,000 squared. Well, 1 over 1,000 squared is 1 over a million. This is e to the negative million. This function is so close to 0. If you keep-
Steve,
Yep.
your mic is really muffled.
Okay. How's it now?
Better.
Okay.
I could hear you.
So if you take x equals 1 over 1,000, you get f of 1 over 1,000 is equal to e to the negative 1 million. That's extremely small. If you do a little bit of work, it's not easy, but it's not too bad. You can show every derivative is 0 at 0. So this is a function that's 0 at 0, its speed is 0, its acceleration is 0, the rate of change of the acceleration is 0. Anybody remember what the change of the acceleration is called?
The change in acceleration.
Nope, there's a name.
Jerk.
Jerk, very good, the
Uh-huh.
jerk. And then after the jerk comes snap, crackle, and pop, like the Rice Krispies. All of its,
Where is that where they got it from?
I think so. So all of the derivatives are 0 at 0, but the function is not identically 0. So for this function, its Taylor series is the function that's identically 0, but f of x is not identically 0. So the whole point of this exercise is to just tell you that the subject can get very difficult. This should not be allowed to happen. You shouldn't be in a situation where you have a function where its speed is 0, its acceleration is 0, the acceleration is 0, and yet it moves. And so the series converges, it just doesn't converge to our function. All right, so have a good Thanksgiving all.